behind the door. Behind
Yeah.
the door. Better.
See.
At the moment,
I'm suffering from a throat problem. I wonder if the people at the back can hear me without talking into the microphone. Yes or no? No. Good. Here we go. The previous papers have spoken at length about sophisticated approach in geophysics to solving problems within the mining area and taking various software routines and up-to-date technologies to produce beneficial results. In the next 15-20 minutes, we're going to be looking at a relatively low-tech area using relatively unsophisticated technology whose proof of concept was established many years ago. However, from observation of the mining industry here to the north, the kind of things we're talking about, which are mainly the maintenance of the walls of tailings dams, the geophysical techniques do not seem to have been efficiently deployed. So we're going to walk through a couple of case histories, which show how you do geophysical mapping around a tailings dam to map pollution pollutants, which come because of wall failure, and come up with a couple of ways to mitigate the issues we see in front of us. The opening slide down on the left-hand side there, that's one of the biggest polluters of all. That's Mount Vesuvius in Sicily, which is spewing out tens of thousands of tons of sulfur dioxide. This, I think Edgar has alluded to this. This is a landside image of the Mary Sprat Tailings Dam. Yeah. And back in 1994, the wall of that failed. You can see the breach point indicated here, and tailings, sludge, and the rest drowned the village of Mary Sprat to the north. There was a court case. The contractors running the tailings dam were taken to court, and one of my guys at the time was called as an expert witness on what can be divined from landsat imagery. And this, incidentally, was the first time that geophysical information has been put up as a major issue in a court case in South Africa. The blue areas, we can see the rectangular tailings dam at the bottom here. The blue areas reflect the moisture content of standing water. And the first thing that draws our attention here is that instead of being localized in the center of the top of the dam, as here, we have the injection point of the water extending to the northeast and ponding against the wall that was eventually breached. One thing that did come up was that analysis of the Landsat data showed that the water was clear, i.e. any particles in suspension had fallen out. And for those particles to have fallen out, the water had been ponding for a considerable period of time. So in the end, I believe the contractors running the dam lost their case. Now, at the time we started advancing to the mining community, they should routinely pick up satellite image data and scan that at regular intervals. It's cheap. Someone can scan it. They can look for the difference between yesterday and today and check if there is any movement along the dam walls or the tailings on top of them. Not sure it's being done because Yankeesfontein diamond mine in the Free State, there was a recent collapse of the dam wall, and here's the breach in here, and the tailings came down the drainage course. I believe researchers from the BITS engineering department are now looking at satellite image data and attempt to see exactly what processes had been incurred. We're going to be looking at terrain conductivity mapping, and the essence of the problem there is that we're looking at the fact that tailings dam water or leachate in waste disposal sites is normally highly electrically conductive. In the first case because of sulfates, and the second case because of other inorganic material. If water escapes from a tailings dam, then it's going to enter the groundwater system, and it's going to mix with that system, and it's going to materially influence the conductivity of that groundwater, which in turn will materially influence the conductivity of the rock that we're looking at. Why are we using geophysics? The major point is that we have this continuous sampling regime. The first investigations of the landside disposal area used widely spaced boreholes, which actually missed the center of the waste disposal of flotsam. However, terrain conductivity mapping of that area did outline in detail. So we got continuous mapping, and particularly in terms of environmental matters, the methods that applied are not invasive. We don't have to dig a hole to see where the major pollution plume is located. That's a particular pollution plume along a river which comes past some mines off to the east. There's a dam in here, and there were complaints from the agricultural community that there were tailings escaping from this dam and contaminating the water in the dam. And of course, cows drinking from that dam died. And of course, they were the farmers' best milking cows, etc. So we covered the area within this polygon here, and we found the largest anomaly was trending along the direction of the river, which happens to be the Elands River, and there was no obvious interconnection between the tailings dam and the river itself. In fact, the river is contaminated by the workings of Rustenburg platinum mines further upstream. But that's another story. What drives this enhanced conductivities? If we're talking about tailings dams, then we're looking at increasing sulfate content, gives rise to increasing electrical conductivity. That's good. We can guess that. How does that affect the rocks in which this groundwater falls? What we find is that for the same electrical conductivity of the pollutant, that the electrical conductivity of the rock increases as the porosity of the rock increases. So in terms of the maximum porosity values of about 30%, if you're looking at a groundwater pollution of the order of about 1,000 ppm sulfate, then the most you might anticipate measuring the field over the rock itself, the formation conductivity is about 100 millisiemens per meter. There are two ways, low-tech ways of approaching the problem. It's an electromagnetic method employing transmitter and receiver coils. The easiest method is usually where the transmitter and receiver coils are mounted at the ends of a boom, which in this case they are separated by 3.8 meters, which gives us a depth of penetration of the order 4 meters.
The
The other method is to connect the receiver and transmitter by a cable whose length can be increased up to 40 meters, and that's going to give us penetration depths for pollution plumes of the order of 20 odd meters there. We're going to take a look at the applications in 2 case histories. The tailings dam in question is this here, and this is the original mine upstream. The red dots, etc., and the blue dots indicate where water sampling has indicated significant contaminated activity, presumably from some leakage point along the dam wall. Now you can see the dam wall, and just below the dam wall is a so-called drainage channel, which takes any water voided from the dam and returns it to a return water dam just down here on paper. That's a closer look at the area. Return water dam is coming down here. It's in that particular sector down there. And the traverse lines to facilitate this survey occupied a 500-meter swathe downslope from the dam wall. Distant lines were separated by 100 meters. Adjacent lines close to the dam were separated by 50 meters. DTM data from the shuttle radar database showed that the dam itself fell between 2 ridges, and that the return water dam just below the face of the tailings dam has various diverging drainage channels, which you can follow as deep, to eventually converge to the west. That's significant. Track that from the drainage channels in dark blue. And we can see continuity from the west coming back to the east to just below the return water dam. And something interesting down here, where no one had really anticipated contaminated groundwater, turn that into a conductivity image of the same data, which are generally preferred by management. And we can see that we have the return water dam here. There's something along the dam wall, some anomalous feature, and we see that the pollution plume is debouching to the west. Again, we've got this feature down in the south here. Back to looking at what's happening here. Return water dam and the drainage channel follows a course up here. This white area here excited some interest because it overlies the major pollution anomaly in the south. And field inspection actually showed it was tailings residue. What happened in this particular area? We did video surveys along the drainage channel towards the return water dam, and one thing became obvious. But first of all, here's a pipe coming out below the dam wall, which is supposed to drain off the tailings water in the direction of the dam, which is just down here. If we walk along the side of the drainage channel, we can see it's all silted up, and it has obviously overflowed to the west, which is why we get the tailings residue here. So the whole area that we looked at was about 55 hectares, and the survey has shown that at least 25% of this is underlain by groundwater pollution. So what? Well, the mine is concerned because most of that area which is polluted is on ground owned by another landowner who is now threatening litigation. So they have a clean-up exercise on their hands. What can be done? The next presentation shows what can be done to at least mitigate some of the effects. This is for a mine, Tailings Dam, which was thought to be intact, but a nearby borehole down here, water sampling indicated about 1700 ppm sulfate content. We went in here with the EM34 transmitter receiver system and used a variety of spacings between the various transmitter and receiver locations. This is just using a simple 10-meter spacing, and the high conductivities are in red and the low or background resistivities are in yellow down here. What we can see over a space of about 200 meters is the broadly advancing pollution front coming out, and then quickly migrating pollution features on here, like two horns of a impy. This raised some curiosity, and fortunately at the time the work was research funded, so we could play around with other geophysical techniques to better define the conduits for the tailings water flow. The top panel here just shows the various responses from color spacings here of 10 meters, 20 meters, and 40 meters. And looking at the difference, one can confidently say that any infiltration of the ground is limited to depths above about 10 meters and no more. Doing further seismic and resistivity work around EM1, the major northern migration path, we've indicated also a depth of about 10 meters for a deeply fractured and weathered zone. So that all ties together. And that's why the polluted area moves more quickly along that zone. Skeptics at the time said, boy, is that really sulfates in the groundwater you're looking at? Is it really tailings water? We deny that. So what we did was to auger two boreholes, one within the center of the pollution area, that's for borehole 760, and another one way to the south in the anomaly pollution-free area from the terrain conductivity survey. As you can see, that's depth down the side, which goes from surface down to 7 meters. As we can see, there's a major sulfate anomaly going with depth, which is about 5 times down depth background. And that appears primarily concentrated in the top 3 meters. There are other complications here, but the mine seized upon this information to say, we're going to put in something called an agricultural trench. Now, this was a new term to me, but apparently what it means is a trench excavated to a depth of about 2 meters. And the idea behind this is that it wouldn't repair the leakage along the wall. What it would do is that it would collect the leakage material and channel the tailings material to a return down. I was skeptical because we've seen that maybe we got a polluted material going down to about 7 meters. Again, we went back, and as it happened, almost a year later, to the day, we went back to the same site and repeated the survey along the traverse closest to the dam wall. Visually, your box is done. You need only look at the top panel here on this. In brown, the shaded brown area is the terrain conductivity profile prior to excavation of the trench. And below it here in khaki is the same profile repeated a year later after any ameliorating effects from the trench. Well, they look significant, but we're all mathematically minded if we're geophysicists, so we decided to cross-plot them here. And right down here, we have year one when we did the original survey, and year two a year later. If you cross-plot the data, if it's the same, you would expect a 45-degree line across going up there, but it ain't the same. It's falling off. And if we look at values which fall within the polluted area, the regression equation gives us a factor of about 62%. So it's possible that the drain itself, going only to 2 meters deep, did divert some of the tailing seepage, diverted it to a return water dam, and the effect of pollution within the area has decreased by about 40%. To put that into context, the first example I showed, which I didn't fully explain, was from the Love Canal site in Niagara in the USA, which was actually the first place that terrain conductivity work was undertaken. And to cut off the leachate escaping from the waste disposal site, they actually dug trenches about 6 meters deep, or even deeper, which apparently worked, and everything, the leachate was deflected in these trenches, and then being very thorough about the whole thing, they then put in a vertical wall just to make sure that everything was properly constructed. Now, a lot of this work goes on in the States, and I see some of the work, the passive seismic that Wayne has spoken about, and other work is de rigueur. In this country, it doesn't seem to be de rigueur. And what we've learned is that we can recommend that we do these terrain conductivity surveys, but until there's an urgent response from the mine or from adjacent landowners that it's a situation normal, don't do anything. Just to put everything in its place, we've spoken about ground surveys. We took part in a survey west of Bits, not too distant from Krugersdorp. And here we see a tailings dam. This is a DTM image. You see a tailings dam on top of a north-facing ridge. And incised into this ridge is a drainage channel descending in the direction of the Krugersdorp Game Reserve. These are extracts from the data which we acquired from the airborne EM and airborne radiometric surveys. Here's our tailings dam, which anyone working in the pits know is full of radioactive material and is also quite conductive because of the sulfates. That's no surprise. What is interesting is this trace here along the drainage channel we've seen on the DTM map, which goes in the direction of the Krugersdorp Game Reserve. And it's marked here by a similar uranium sinuous feature, which goes in the same direction. We were all set to do the interpretation when the client canceled the project at this stage, because what happened was that this acid mine drainage material was getting into Krugersdorp Game Reserve, killing hippos, or at least sending them blind, and eventually the game reserve closed because of that, plus other factors. So there is a potent effect, and it is one of the reasons why there should be active, proactive monitoring around these features, not just when a nearby neighbor starts threatening you. Okay, the main thing is with terrain conductivity mapping to generate a environmental hazard maps, of which previous speakers have spoken. And they give you this comprehensive coverage that you can't get between widely distributed boreholes. The boreholes are useful because they're the only ones in which you really obtain subsurface rock and pollution samples. But what you need actually is a judicious combination of geophysical surveys and surface, and coupled with a drilling program which focuses on the anomalies revealed by the geophysical surveys. It's not all easy though. There's an example around a tailings dam up on the Bushville, and you can see it's normally characterized by low values, less than about 20 millisiemens per meter. So no problem. However, we have an enhanced value here of about 40 millisiemens. Immediately, the uninformed observer can throw up their hands and say, boy, you got a pollution leak here, and could start a little march for investigation down in this southwest corner. The truth of the matter is, this was a baseline survey done before the dam was in operation. So there are no tailings within it. And hence there's nothing to escape. And the further truth of the matter is that this red anomaly down here actually reflects shallow clay deposit very close to the surface there. And that has given the response. So, once you've got your pollution mapping results, think about what the geology might do in the way of putting together conductivity anomalies due not to pollution, but due to features like clay layers, etc. Right. Once upon a time, the engineers used to call us battery-operated geologists. Now I think we have all as a community emerged well beyond that status. Thank you.
Thanks, Geoff.